into this equation over here. So we have this equation, stress A squared minus stress A stress B plus by stress B squared, and the whole thing must be equal to stress U squared. Okay, so this is based on analysis. This is based on material property. Okay. So we substitute stress A is equal to minus stress B. So stress A squared, right? So plus by stress A squared plus by stress A squared. Let me not skip step, okay? So this is minus stress A multiplied by, so stress B is equal to minus stress A, right? And then stress B squared is going to be positive stress A squared. This is equal to stress U squared. So when you multiply all of them together, or add them all together, you have 3 sigma A squared is equal to stress U squared. So therefore, stress A squared is equal to stress U squared divided by 3. And finally, stress A is equal to stress U squared, or stress U divided by square root 3. So 1 divided by square root 3 is equal to 0.577. Okay. So this is the first thing. Okay. So we have done one factor y. So the next thing we're going to look at is the second factor. I'm going to try to squeeze all onto. Okay, I will not squeeze. Okay, I'll just copy, and we go to the next page. Okay. So we have to also consider. Okay. So the second factor is we have to also consider the stress state along line CD. Okay, line CD, as in this line over here, is our line CD. Okay, so this line that I'm going to highlight, this is our line CD. So at what stress state do we is our Mohr circle represent on line CD? Okay, so let's look at this. Okay, so we know that we have to meet the condition where stress A is equal to minus stress B. Okay, and we are also aware that stress A and stress B are principal stresses. Nothing new, right? Principal stresses means shear stress is equal to 0. So now we're going to sketch Mohr circle. Right, we're going to sketch Mohr circle. So this is our normal stress, and this is our shear stress. Element rotate clockwise, element rotate anti-clockwise, and then I'm going to draw our Mohr circle. Okay, that looks about right. So this will be our stress A, right? And this will be our stress B. Okay. So we know that the stress average has to be 0. Okay. So in what condition? Okay. So we are going to have, so I think I did ask this in the quiz before, okay, and a lot of you got it right. So in what stress state okay, in what stress state where stress average is equal to 0, right? And stress A must be equal to minus stress B, right? So we have condition number 1. Okay, condition number 1. If we have our structure under pure shear, okay, if we have our structure under pure shear condition, right? Shear XY, here's shear YX. Okay, so I'll draw transformation. This is X, and this is Y. Okay, so for this case, right, when we construct mole circle, we will get what we see on the left hand side. Yes or no? Right. So I'll write over here. So condition number 1, shear XY is equal to shear YX. Stress X is equal to stress Y, and they are all equal to 0. And then we have condition number 2. Where we have a situation, okay, so the same element, right, and we have our normal stress at our yield, or not necessarily at our yield, where we have stress, this is at yield, okay, not necessarily, this is our stress X, this is our stress Y. Again, we have a condition number 2, where stress X is equal minus stress Y, okay, stress in the Y direction. And you have shear XY is equal to shear YX is equal to 0. Okay. And then you have a third condition. Okay, you have a third condition. Again, you have stress X, stress Y, and then you have a shear. Okay. So again, if you have condition number 3, you have stress X is equal to minus stress Y, shear XY is equal to shear YX, and they are not equal to 0. Okay. So all these will yield the mole circle looking like this in these 3 conditions. And I'm so glad we have this in the quiz. It's so easy to explain to you guys. You guys can actually understand. In fact, in the quiz, I make it worse. I make it what? 3D, yes or no? Was it 3D? Yeah, it was 3D, right? So now you'll understand what I mean now, okay? So most of the time, okay, right? If you have done, remember when we do combined loading, when we do shaft, right? Most of the time we only have one normal stress. You all realize that, right? And then we can include the shear, right? Very seldom when we do our compound stress analysis where we have condition number 3, yes or no? Where we have stress in the X, normal stress in the X, normal stress in the Y, and you have shear, right? So this condition is very common, right? The one that, so this is under pure what? Torsion. Okay, this is the, so what I'm trying to say is this. If you were to calculate, okay, during torsion, during torsional analysis, okay, which is condition number 1, okay, the recommended torque proposed by von Mises will be larger compared to Tresca, okay, or the recommended diameter proposed by von Mises will be smaller, okay, compared to Tresca. Okay. So the applied torque will, if we look at applied torque, okay, it will be larger using von Mises. The recommended diameter will be smaller because it's more aggressive. Yes or no? It's less conservative. Okay. So enough of me yapping. Now we are going to look into a combined loading situation. Okay. So this I have posted on Avenue to Learn last week. Okay. So this is, I'll let you guys copy first. And we will not be able to do the problem. I'm just going to introduce the problem to you. Okay. And we're going to draw the element. I think we can start sketching the element. It's quick. It's like 5 minutes thing for you guys now, sketching the element. Okay. Okay, let's look at an example. So we know the theory now. Okay, let's look at an example. So if you were to look into last week, what's this problem over here? You can find on last week's notes, okay, on a Friday, on the example. Okay, we have a shaft 1.5 diameter of steel with a yield strength, okay, of 42 KSI. So we are given that the diameter is equal to 1.5 inch. And the yield given to us is 42 times 10 to the power 3 PSI. So using the maximum shear stress criteria, determine the magnitude of the torque for which the P, okay, so the axial load, so if you were to, the P is equal to 60 times 10 to the power 3 PSI. So we have to determine the torque. So for this question, they want us to use maximum shear stress. So maximum shear stress, we know that it's Tresca. But more important, we're going to do the example of maximum distortion energy. Okay, so they also want us to calculate based on maximum distortion energy, which is for Mises. Okay, so you can see how I don't mix up with Tresca, right? And von Mises. We know Tresca, shear, I use tau. Okay. Okay. So now, if we were to put an element down here, okay, if we were to put an element down there, and we're going to call this direction X, going up, it's Y, this is Z. Okay, so if we were to draw the element out, right? If we were to look at the stress state, we know that stress, we will have a stress coming down, that's Y. And then the shear, because the torque is applied this way, the material want to move in this direction. Okay, material movement, material movement due to, hey, Eugene, come on, due to torque. Right, so we know that the shear will be acting in this direction. Okay. And then the rest of the stress field, okay, we know that stress X, normal stress X is equal to 0, normal stress Y is equal to 0. Okay. So from here, Wednesday, we will sketch 3D mole circle. Then from 3D mole circle, we're going to apply Bomisi's analysis. Okay, and it's not difficult. Okay, this is the easy part. Okay, this 5% part in the analysis is the easy part. Okay, but I think the highlight over here is to explain to you how the criteria is developed. Okay, as I said, he is very practical. Okay, I'll see you guys on Wednesday.